Hello. So today's topic will be I will be solving the problems on steady flow energy equation, which is the first law applied to open system. Basically, there are so many applications in engineering thermodynamics which are mainly coming under open system. Example: turbines, compressors, and nozzles. And as we say, steady flow energy equation, a steady flow process wherein the properties will not change with respect to time, and the boundary work is zero for such steady flow systems, and the total mass or the energy entering the control volume must be remaining the same. The energy at the inlet is equal to energy at the outlet. This shows a general open system wherein I have taken a control volume. With some reference, I have shown the potential energy, internal energy, the kinetic energy at the inlet as well as at the outlet. Just to show, there is work output from the system W and heat interaction Q within the control volume. Now I am supposed to write the energy balance for the system. Basically, for steady flow system, the amount of energy entering a control volume in all forms should be equal to the amount of energy leaving it. If I just see this equation, E in minus E out, the change in energy with respect to time is equal to 0. Hence, E in is equal to E out. For a non-flowing fluid, I have three energies: internal energy, kinetic energy, and potential energy. Whereas for a flowing fluid, I have enthalpy, which is the sum of internal energy plus flow energy. A flow work is nothing but it is the energy required to push the mass into or out of the control volume. So just it is the inlet wherein the fluid is pushed to a distance L. The flow work is nothing but force into the length which is pushed. So force can be written as pressure into area, and which is equal to PV. So as I told in the previous slide, the energy, the total energy of the flowing fluid per unit mass is given as this: U plus KE plus PE plus PV. So this is enthalpy, kinetic energy plus potential energy. So all taken as kilojoules per kg. So the final equation for this steady flow system, E in is equal to E out. So just when I write this, I have U1 plus P1 V1 square by 2 plus Z into Z1 plus Q is equal to W plus U2 plus P2 V2 plus V2 square by 2 plus Z into Z2. So U1 plus P1 V1 is nothing but H1. Similarly, U2 plus P2 V2 is H2. Rearranging this will give Q minus W as H2 minus H1, V2 square minus V1 square by 2, Z into Z2 minus Z1. So where Q is the heat transfer across the control volume, W is the shaft work, V is the velocity, Z is the elevation, and G is acceleration due to gravity. So again I can write on rate basis by taking m dot and q dot. So this is kilojoules per second, and this term is also in kilojoules per second. Similarly, this is also kilojoules per second, and this product is also in kilojoules per second. For an incompressible fluid, I can say mass is equal to rho AV. Since m1 is equal to m2, I can say rho 1 A1 V1 is equal to rho 2 A2 V2. So this equation is generally called as steady flow energy equation for single inlet and single outlet. So students are advised to remember this equation in terms of rate form or in terms of kilojoules per kg as shown in the figure. So basically, as I was telling you, open systems are used like nozzles and diffusers, All these are the examples of open systems: compressors and turbines, throttling device, mixing chambers, and heat exchangers. So let us just apply this equation for what do you call nozzle or diffusers. For a nozzle or diffuser, definitely if it is adiabatic, Q becomes 0. So for them work will be 0. They are not producing any work. And since they are horizontal, Z1 becomes equal to Z2. Hence the equation becomes simplified as H2 is equal to H1 minus V2 square minus V1 square by 2. Or basically for a nozzle I am interested in V2, which will be much greater than V1. For a diffuser it is reverse. V2 will be much less than V1 as shown in the figure. Similarly, if it is for compressor, if it is adiabatic, WQ term becomes 0. For turbines and compressors, I can write the equation like this. For turbine, left hand side I have just taken Q0, assuming it is adiabatic. So basically I am interested to find out W. So for a turbine, most of the times these kinetic energy terms will not change much, and also potential energy terms will not much change, and they are negligible. So the work output from the turbine will be in terms of enthalpy at inlet minus enthalpy at outlet, that is H1 minus H2 into m dot. Similarly, there is a device called throttling device, wherein what happens, the fluid is made to flow through a constricted passage. So because of that, its pressure and temperature gets decreased. For a throttling device, Q will be 0, W will be 0, potential energy term will be 0, and kinetic energy term will be 0. Hence for throttling, enthalpy before throttling is equal to enthalpy after throttling. So this throttling process is used especially in refrigeration, either in terms of capillary tube or in terms of expansion valve.